Why is it not electrical?
That's coffee. Coffee is just like a flower. So you drink it.
Are you all able to?
People now used to call it.
Okay, so are you all able to access the videos for this class or no? Because at my end it shows not available, but then when I click it, it is available. So can you, has anybody checked? Yes? Okay, so a few updates. I think data collection is going to end today. So, a lot of groups couldn't do 20 gestures, but I think all the groups have done at least 10. So what we'll do is we'll release the data for 10 gestures and we'll go on with assignment 2. So I will upload assignment 2 today or tomorrow and we can start doing it. Now, the rest of the data will be needed for assignment 3 and 4. So we'll have to schedule again. This time it will be much shorter. It won't take 1 hour. And we'll keep 1 hour slots, but I think it will be done much faster.
Yesterday we could not do the recording.
So any questions you have?
Do we have to do it again because we just did like 5 gestures?
Oh, so yeah, if you have done 5, we will do 5 more. But that is later. So whoever hasn't done 10, we will reschedule them and we will do at least 10. What? We will need that for assignment 3. So when we do assignment 3, we will reschedule. Any other questions? Okay, so let's continue our discussion. We are trying to discuss support vector machines. And we discussed a little bit. We didn't discuss the slides, so we discussed some basic concepts and then we came on to support vector machines. And we said that support vector machines are maximum margin classifiers. And we discussed some intuition behind why maximum margin classifiers are good. Or not good, but why SVMs consider maximum margin. And that's what we discussed last time. Okay, and then we are trying to figure out the math. So let's continue to figure out our math, right? Although it's not that difficult, but still, let's quickly go over this, and then we'll talk about other things. So, so we have to find a line, right? And a line is described by these two parameters, W and D. W is what? The slope, and B is the bias. Now W is a vector. Why? Because we are doing the summation over X. And if this was just two-dimensional, it would have been easy. But if it is three-dimensional, then W becomes larger and larger and larger. Right? So we have to find out W. So one property of W is that it is perpendicular to the line of separation. Why? Because of that. We already talked about this. Because any point on the line, you should satisfy those equations, Wx plus B. And from doing some algebraic manipulation, vector manipulation, we found out that W has to be perpendicular to the direction of that line. It has to be perpendicular to the line. So that is one thing. Now let's try to figure out W. So now what we said was that ideally we would want a margin. Let's say that margin is epsilon. Let's say we don't know the value of the margin. Now what we argued was that the function of SVM is to classify. It is to classify into two classes. So we said that okay, why not we just so let's have the class levels as 1 and -1, right? And why not find a W such that epsilon becomes 1? That will make our lives easier. Right? So if epsilon is some random value, maybe 0.5, 0.23, instead of that, if we find a W such that epsilon becomes 1, it's just a matter of scaling. Right? So if it's just a matter of scaling, then it doesn't take away anything from SVM. It will still be the maximum margin classified. So that's why we said that okay, let's consider that the class boundaries or the closest data points to the line, let's say that is Wx plus B equals +1 for the class that is +1, and the closest data point to the line for class -1 has Wx plus B equals -1. And what we'll do is, we'll try to change the angle of this line so that the +1 and -1, those margins increase or decrease. Right? And we would like to have the maximum margin. So now note that we are not changing W. Rather, we are selecting support vectors that change W. So what is support vector? Support vector is the points that are closest to the line. And those are the support vectors and they define the line. So that is a fundamental thing that you have to know, that we are not selecting W. We are not changing the slope of the line. What we are doing is we are selecting support vectors that give us the line. So now let's try to analyze this. So we know that any data point that is on the +1 class and is on the margin, that will have Wx plus B equals 1, and any data point that is on the -1 class and is on the margin will be Wx plus B equals -1. And we did this calculation and we figured out that the margin is 2 divided by the L2 norm of W. That's what we figured out by doing some algebraic manipulation. So which means we have to maximize the margin D. So which means we have to minimize the L2 norm of W. So we can potentially figure out, I mean, the reason we are doing all these equations is that we want to represent the SVM learning as some form of this optimization problem. That's what we want to do. Right? So that's why we want to first figure out the objective function. Maximizing the margin means minimizing L2 norm of W. So we figured out the objective function. Now we have to figure out the constraints. So if it is a linearly separable case, what is the constraint? The constraint is, if I have a data point in class equals +1, I should have a W and B such that Wx plus B is +1. It should never be the case that I have a data point which is the +1 class and Wx plus B is -1. Right? So it should be at least b plus 1 or more. On the other hand, if I have a data point that is in the minus 1 class, wx plus b should be at least minus 1 or more. It cannot be less than minus 1. So those constraints are true for the linearly separable case. Why? Because we know that there is such a line. We know that there is such a line. So we don't want to find any other line. We want to find a line which such that wx plus b is plus 1 if x is in the plus 1 class, is greater than or equal to plus 1, or wx plus b is less than or equal to minus 1 if x is in the minus 1 class. We want to have that line. So if we want to have that line, we can represent that with a single equation. What is that equation? This. So that is what it is saying, that wxi plus b, if it is greater than 1, only if yi is equal to 1, and wxi plus b is less than or equal to minus 1, only if yi equals minus 1. So the constraint, we can combine these two to give this constraint, and yi multiplied by wxi plus b is greater than or equal to 1. Right? We can have this as constraint. Now what type of constraint is this? Linear, non-linear, or what is it? Is it a linear constraint? Note that if you have yi and xi as different, yes, it's a linear constraint. But you have to note that what is yi? Yi is the class label, right? So if it's yi is a class label, yi is one of the columns of x, right? Don't understand.
Why is class?
What was our definition of classification? We said that we want to express the class attribute of data as a function of other attributes. So which means class is an attribute. So class is a part of x. It's another dimension of x. But yes, if you define another variable yi, which has the class labels, and yi is 1 if it's plus 1 class, and yi is minus 1 if it's minus 1 class, then this is linear. So now we have to solve this problem. So we have to minimize L2 norm of W. Now the thing is, L2 norm of W has square root, right? So we want to avoid that square root because we want to formulate this as a quadratic programming problem. So that's why you square the W. So you now want to minimize W squared by 2, and the L2 norm of W squared by 2, and the subject to the constraint that yi wxi plus b is greater than or equal to 1. Right? So that is the deal. Now we can simplify this problem further if we use some Lagrangian multipliers. Now that is a little bit of a different concept. So how many of you are familiar with Lagrangian multipliers? Not many. So should I discuss? Okay, let's. I won't go into the mathematics, and I can go into mathematics if needed. But let's not go into the mathematics for now. But if you don't understand, then we will go to the mathematics. So first of all, why is Lagrangian multipliers needed? Yes.
To convert a constrained optimization problem into an unconstrained optimization problem.
I mean, partially correct. Why? Because you see there is a constraint. Lambda I is greater than or equal to 0.
That's constraint of Lagrangian multiplier itself, I guess.
Yes. So it is constraint optimization. It's not unconstrained.
We don't have any constraint on W now. W or Y.
Why do you not want a constraint on W or Y?
It won't let us search our entire search space for W. So we won't be able to.
Anyways, you are not searching the entire search space for W because you have some constraints, lambda I.
Still, it's more than what we were searching.
No, so unconstrained optimization is not useful. Right? What you can do is you can have a W0. It's unconstrained, W0, no constraints. Right? But that will minimize. That will minimize mod W square by 2, right? If you have W0. But that won't give you the line. Why won't it give you the line? Because it won't match the constraints. Yi wxi plus b greater than 1 won't match the constraints. Right? So that is not unconstrained. Lagrangian multiplier, you don't use it for unconstrained. Thing is, you are including the constraint in the objective function and you are having a simpler constraint, lambda I. Right? And the thing that I agree with you is, you are not, in the constraint, you are not including the objective. You are not putting a constraint on the objective function directly, but indirectly you are. Right? But this is a much simpler constraint. If you look at lambda space, so lambda is some variable, right? So basically this is transforming the variable. Instead of asking you to find W and B, it is asking you to find lambda. Right? If you find lambda, then I can express W in terms of lambda, I can express B in terms of lambda. So it is telling you, okay, find lambda, you don't have to find W and B. Right? So find lambda. So now, if you look at the whole search space of lambda, you want to find a lambda, and if you look at the whole search space, so lambda I is what? It's like a real number, right? It's the coordinate space, big coordinate space. Now, what does this constraint mean? Lambda I is greater than or equal to 0 for all lambda I. It's just the positive half plane. Okay? So, if it is the positive, it's just simplest constraint. The constraint has been simplified a lot. So that's why you use Lagrangian. You are changing the parameter that you want to find out. So if you consider the first problem, what is it saying? It's saying that find out a W and B that minimizes the norm. So your output is a W. So which means your output is closely related to your objective function. Typically, your objective function is a multiplicand of your output. Right? If you look at this, if you look at our optimization formulation, let's say the simpler one, this is not the one that we are doing, but this will get the point across. So if you look at the objective function, what is it? C transpose multiplied by X, right? So your objective function is a linear multiplicand of the value that you are trying to find. But if you come here, even for the quadratic case, linear multiplicand plus X transpose. But if you come to L2 norm, you cannot get it from X transpose. It's not in that form. Right? But this one, if you use the LP, the Lagrangian multipliers, your objective functions, the constraints get included in the objective function. So see this constraint Wi, Wxi plus b, this is included in the objective function. And they're telling you, okay, find lambda i's. So if you find lambda I, see it is just a multiplicand of lambda I, the objective function. Right? So it falls in the same form that we are familiar with. Now it turns out that you have a relation with Wi and lambda I. You can figure out a relation with Wi and lambda I. So how can you figure out? So okay, now you have to do some math to figure out why W is this and why this is summation. So what you have to do is you have to find the differential of LP with respect to W and differential of LP with respect to B and make it 0. And then you'll see that W becomes this, and this constraint also arrives. So now I'm not going into that details. If you don't understand, like if you go home, like read it, if you don't understand, then next class I will go into the details. Okay? But for now I am skipping it. So then what happens is that you, instead of solving this big constraint problem, you solve another constraint optimization problem. It's not unconstrained. You solve another constraint optimization problem which has this is the objective function, and this becomes your constraints. So if this is the objective function, you see this is linear plus quadratic. This is the quadratic programming problem. So from this weird expression, we came to a quadratic programming problem. Now you solve it using whatever program you want to use in MATLAB. Okay? And then what you get? You don't get W and D. You get lambda i's. Right? Lambda i's are the multipliers, the Lagrangian multipliers. And then what you do? You use this equation. You know yi, you know xi, you know lambda I. So you can easily figure out what is W. And once you figure out what is W, you can figure out B. How can you figure out B? Use the constraints. You know lambda I, you know W, you know y, you know xi, and you know that this constraint has to be met. So you can figure out B. So that is how the training part for support vector machines. That is how you train. Now the thing is, for a training set, you get one W and one D. Right? Now for a training set, you can get multiple W's and multiple D's as well. Why? You cannot get multiple W's, you can get multiple B's. Why can you get multiple B's? Because you know that there are two constraints. Yeah, right? Two constraints. So if this is greater than 0, then 1, and if this is less than 0, then minus 1. From these two constraints, you can get two different values of B. Which one you choose? It's your choice. You can either choose one of them or choose an average of them. It's your choice. So then it gives you this examples. So here it gives you an example of two different two-dimensional example. Right? So let's go through the example, because I won't ask these in the exam, but still let's go through the example. So they have done the optimization and everything, and they have given you the multipliers, the Lagrangian multipliers. So these are the Lagrangian multipliers. So now how do you find out W? Basically just take the lambda i's and do this summation. So these are all zeros and these have some values. Right? So you multiply it and you found out that W1 is 6.64. It's very easy. So what you do? Lambda 1, 65.52 multiplied by yi, which is 1, and multiplied by xi1, so 0.3858. Right? And then you do this for the first dimension. So for the first dimension, you only are worried about x1, y, and the Lagrangian multiplier. For the second dimension, you are worried about x2, y, and the Lagrangian multiplier. So you figure out W1, W2. Now again, as I said, that for the two dimensions, you can get two different B's. Right? So from the two dimensions, you apply these equations. You figure out two different B's. You can take any one of them, or you can find an average. So that is how the SVM works. Now the thing is, we have understood the case of linearly separable case, which means that there always exists a line. So if there exists a line, we have found a solution where we will find that line. Now what if there is no line, no such line? So not the non-separable cases. Now this is kind of contradicting, because we have said that just increase the dimension and it will be linearly separable. Right? So why don't we do that? Why don't we just increase the dimension and it becomes linearly separable and we don't need to do non-separable case? Why do we have to understand non-separable case? Because what we see is that it's just a quadratic program, right? So solve it. What is the problem if I have multiple dimensions? Yes, so yeah, that the reason is trivial. I'm surprised that why so many lost phases. Right? So reason is simple, as he is saying, that it will lead to overfitting. Why? Because how will you increase the dimension? You will increase the dimension by doing some transformation. Right? Maybe that transformation is too simple. I mean, there is no characteristic transformation of the data. Maybe in order to increase dimension, you have to lose information using that transformation. Right? So if that is the case, then even if you can optimally solve the higher dimensional problem, still it's not of any use. So, and often the quadratic program in high dimension increases computation time. The training will become more and more complex. So what you can do is have some suboptimal solutions. Don't have a line, and don't have the exact line that separates the two data points. So if you don't have an exact line, what will happen? There will be some errors. Errors means false negative, false positive. There will be some sort of errors. So, but as we have seen from a discussion and generalization error concept, that we don't want a machine to be 100% accurate in training data. Because that means that it is learning the noise and it is most likely to be erroneous for test data. So anyways, we don't want a machine to be 100% accurate. So if it is not accurate, that's fine. So that's why we need to learn the non-separable case. For many reasons, reiterating. One reason is if I increase dimension, the solving the quadratic problem becomes more difficult, it becomes more complex, time consuming, it may have errors. Second is the transformation that I am using to increase the dimension. How am I sure that that transformation is practical? It will not lose information. How am I sure? Right? So that transformation may lead to loss of information, and that might lead to wrong classification. Right? That is the second thing. And what was the third thing? Oh no, not over. So anyways, we don't want the machine to be 100% accurate on our data. Right? Because this is training data, this is not test data. So we don't know how the test data is going to look like. So even if I train an SVM which perfectly classifies training data, a test data might come in which totally disagrees with the classification. Right? So that can anyways be possible. So we don't want that. So that's why we need to learn, talk about the unseparable case. It turns out that the unseparable case is not that difficult. It's a simple extension of the separable case we can make. So instead of having a hard margin formula, so what is the margin formulation? The margin formulation is, we say that okay, if x is belonging to +1 class, then it has to be wx plus b greater than equal to 1. Right? And if the training data is x is -1 plus -1, then it has to be so that wx plus b is -1, greater than equal to -1. That is hard constraint. Right? Now what is a soft constraint? Soft constraint is that, okay, I say that, okay, let's say that wx plus 1 is not greater than equal to 1. Let's say that wx plus b is greater than equal to 1 minus epsilon. So there is some slack. And you include this epsilon in the optimization. So you reduce epsilon. So you do this trade-off. Okay, do I allow a little bit of data points to be below 1? Right? And can I reduce the difference between the points that are below 1 and the margin? Can I reduce the difference using the optimization? So there is a trade-off. How much slack you allow versus can you reduce that slack? Right? So you have slack variables. So this is zeta i's. These are slack variables. Right? So introduce slack variables. So how does it affect your object? It doesn't affect your objective function as such, but it affects your constraint. But we would also want these slack variables to appear in the objective function because we want to reduce them. Right? So initially it appears in the slack. So it says that okay, if xi belongs to the +1 class, let's cut it some slack. Let's not make wxi plus b greater than equal to 1. Let's say it's greater than equal to 1 minus some zeta I. Now this might so happen that zeta I is greater than 1. Right? If zeta I is greater than or maybe greater than 2, then what happens? Weird things will happen. Right? Even if the data point is -1, it gets classified as 1. Right? So that we'll discuss. We'll talk about that. Now, slack variables, we force them to be greater than equal to 0. So we will have to force them to be greater than equal to 0. And we want large values of slack variables to be penalized. We don't want large slack because we want to avoid this. That data which is -1 gets classified as 1. We want to avoid this. That can only happen if zeta I is greater than 1, right? Or greater than 2. If zeta I is 3, then wxi plus b is greater than equal to -2. So it can be less than -1. So in that case, a class which is negative class gets classified as positive class. We don't want that. That's why we want zeta i's to be very small. Right? So we want to penalize. We want to penalize you from using a lot of slack. So what we do is we include that in the objective function. So we modify the objective function. Right? So now previously it was L2 norm w squared by 2. We want to minimize that. But now we also want to minimize the some function of this slack. Now what is the function? You can either make it linear, you can make it to the power k, or it depends upon your choice. Right? So c is a constant, c and k are parameters that give you penalty. Right? And if you have too much zeta I, then if you do the power of k, that is a very big value. Right? So that's why it gives a penalty. So c and k are penalty parameters. And these are called penalty for misclassification. Why is this misclassification? Because as you increase zeta I, there is always a chance that minus points which are in the negative class gets classified as positive class. So that's why it's called penalty for misclassification. So now if k is very large value, then this becomes, k is greater than 2, then this is a more complex problem. It's not even quadratic programming. It becomes worse, and complexity increases. So, but if you make k equals 1, then it is nice and easy, linear. Right? So it becomes quadratic programming because it's quadratic in W. So now you can do the same thing. You can, in order to simplify the constraints and include them in the objective function, and to make the objective function just a product or a quadratic function of the parameters that you are extracting, you can use Lagrangian multipliers here as well. Right? And it turns out that the formulation is not that difficult. Oh, the slides don't show the formulation with the Lagrangian multipliers. Yeah, so let me do one thing. Let me discuss SVM. Next class I'll discuss the mathematics behind the Lagrangian multipliers. What happens when we use Lagrangian multipliers? Right? So, and why do you use it? And there is this notion of primal and dual problems. So these we shouldn't discuss in data mining class as such, because these are concepts of algorithms, advanced algorithms and all that, optimization. Right? But I'll spend some time. I'll spend some time maybe next class. So now we are going towards non-linear support vector machines. So we are now moving towards something called kernel SVM. Right? So the previous example, the previous formulation, whatever we did it on the attribute space. Right? We got the attributes X and we didn't do anything to it, and we tried to do SVM on it. Right? Now we are saying that, okay, what if there is a non-linear SVM? So this is one example that if you increase the dimensionality, you can figure out linear. Right? So this is an example. I think we used this example before, right? If the data is projected to a higher dimensional space, there is a good chance that the data will be linearly separable. But the problem is, how do you know this transformation? This transformation is not always known. Right? You can see here. Here it can be seen. So you understand that you have to do some x square plus x2 square. But often this is not that intuitive. So yeah, so that's why if you classify in the higher dimensional space, and then when you come back, it becomes a nonlinear function. Okay. So that is one way to have nonlinear SVMs. So this higher dimensional space, you can, it's also called, and it has different names, right? One is feature space, you can add more features. Another is kernel space. Instead of adding more features, you just apply some transformations on the features. And the other is, it's called Hilbert space. Hilbert is a very specific type of function. Again, I don't really want to go into it. Right? So these are concepts which might be like you may not understand right now. So if you want, then I can discuss. But I don't want to get into these. That's the problem. Because these are all discrete math concepts. Hilbertian space. The kernel space, as you know, is just the kernel. You do the transformation and you go to a different dimension. Right? Okay. So I need to talk to you about Lagrangian multipliers. What is the math behind it? Then I need to show you the math behind slack variables and the math and all these Hilbert space and new things. So I'm not sure whether that will be any use to you or not. So that's why I'm not trying to discuss this. But let's see. So now the problem with having increasing dimension is that yes, if you increase dimension, then we have curse of dimensionality. And it does not mean that, it does not simply mean that you are increasing the complexity of training. It's not that simple. What we have seen before, now I am reiterating, that if we have higher dimensionality, then the amount of space that is interesting to us, that reduces. Right? So, but the machine searches the entire space. So this becomes more difficult for the machine to find out interesting data. And so that is another problem with curse of dimensionality. So that is what, if you go to a kernel space, that can be a problem. So don't increase the dimension too much. So in the nonlinear sense also, you can use Lagrangian multipliers, okay, in the nonlinear sense. So this gives a comparison between how you can go to nonlinear space. Right? So if you go to nonlinear space, what you see is that instead of this problem, this is the original problem that we solved. Instead of this, we are just solving this problem in just a transform domain. and we are just doing a transformation on X and just doing SVM in that domain. So we are not doing we are not solving the problem in the X domain, we are solving the problem in the phi X domain. So how does it look like? So the dual problem, again I haven't explained what is prime or dual, maybe I can explain next class. But the dual problem is this: instead of solving this, minimizing this, you are minimizing this one. Right? So if you are minimizing this one, you see that you need to understand the dot product in the kernel space. Right? So phi is the kernel, the function that you are using to transform your data. Right? So you need to figure out dot product in the kernel space. That is the most important thing. Why? Because if you want to predict a test sample, you will use this equation, and this equation also has the dot product in the kernel space. So you only need the dot product, you don't need phi. So now what you can do is you can apply something called a kernel trick. Right? So what is the kernel trick? The kernel trick is that instead of applying the kernel transformation on individual data points, what you do is you take two data points, the test and the train, test data point and training data point, and apply a kernel that gives you the dot product in the kernel domain. Gives you the dot product. Instead of giving you phi x and phi z individually, you apply the kernel to get phi x dot phi z. Now the problem with that is, given the kernel, you cannot figure out phi. That's a big problem. Typically kernels are radial basis function, or maybe if it's polynomial it is easier to figure out. But if it is the radial basis function, it's difficult to predict or figure out the individual phi's. Okay? So you use the kernel trick to make your life simpler, but then you cannot figure out the phi's. So if you cannot figure out phi, what will be the problem? Why do you need to know phi? In order to do classification, you don't need, right? If you want to use the SVM to just do classification, you don't need phi. Why don't you need phi? Because if you see, predicting a test sample needs just the dot product. So if there is a function that gives me the dot product in the kernel domain, given two values, xi and z, it gives me just the dot product in the kernel domain. Why do I need to know phi? So for classification, I don't need to know phi. But there are certain cases where you need to know phi. And this is a practical example. So let's take a practical example where you need to know phi. So you know biometric authentication systems. Now we are going a little bit tangential, but this will establish a very important problem that is still under research. So the research is going on in this problem. So let's say I have a iPhone 10. Okay. iPhone 10, is it still in the market? People are buying? Yes. Right. So iPhone 10 has face recognition. Right. You take a picture of your face and it says authenticated. Now let's say it uses some machine learning system. It uses some machine learning and some signal, a mixture of these two. Right. So it uses some machine learning technique to figure out whether you are the person you claim to be or not. So authentication. Now let's assume that it uses SVM. I don't know whether it uses SVM or not. Right? Now let's assume it uses SVM. So what will an SVM do? So we are talking about face recognition. Let's assume that it is using SVM. So what will the SVM do? Let's say it has face images from a lot of other people, right? And let's say this is the so from face it extracts say hundreds of features, but let's assume that it only extracts 2 features because we want to show it on paper. Right? Let's assume that it extracts 2 features, and let's assume that F1 can take a maximum value of this, and F2 can take a maximum value of this, and the minimum value of F1 is this, minimum value of F2 is also that. Let's assume. So which means that all features from anybody's image will lie in this box. Right? And this box is huge, let's say. So all features are lying in this box. So what will the SVM do? It will have 2 classes. So these are all face images from a large number of other people. Right? And this is a feature from your face. You are the iPhone 10 user, let's say. Now it has only one sample of you and a lot of samples of others. Now this SVM, the mechanism, face recognition mechanism gets more and more accurate as you use it. So which means that it takes your picture and it creates more feature points. Right? Creates more feature points. Now if you are using SVM, then what you will do? You will figure out a line or maybe at least a curve, let's say. Let's say this is kernel SVM. Right? And you don't know the transformation, so you don't know this line. There is no way for you to know this line because you don't know the kernel transformation, right? Now the thing is, so this is the iPhone 10 system. Now let's say I'm a very person with malicious intent. So you are using your facial image to get into your phone. I want to get into your phone. And if I use my image, it will fall somewhere here. Right? It will fall somewhere there. So I don't know. If I use my image, it will reject me. Now what I do is I try a lot of images. I try a lot of images. Not only mine, maybe some other person, or maybe an image of a donkey. Right? So let's say this is a donkey. Donkey was classified here. Now, can I make some changes to this donkey image so that it looks like you? The thing is, it doesn't need to look like you. That's the deal. It doesn't need to look like you. It doesn't need to look like any human being. It might be an absurd image, noise image. But can I make some changes so that this donkey image moves here, somewhere here? That's the only thing that I need to ensure. So this image doesn't need to look like a human being, doesn't need to look like you, doesn't need to look like a donkey also. It's just some noise image. But what it does is that the features that are extracted just goes beyond this line. If it goes beyond this line, doesn't matter whether it's your image or not. It will get classified as you. Right? So that is a threat. That is a threat to your face recognition system. And why is it a threat? It's because SVM is not learning you. It is learning a huge space in which your features are a small part. So this will become even more and more dangerous if you include more and more features. Because if you include more and more features, then that means the irrelevant parts are increasing. So your features becomes a smaller and smaller part of the entire space that SVM classifies. Right? And if that becomes smaller and smaller, it becomes easier for an adversary to take an image of a donkey and make it you. Right? So now this is a new domain of research that is going on. It is called adversarial machine learning. Adversarial machine learning. So which means that now a person is trying to attack a machine. When a machine is used in some form, maybe in authentication, maybe some image recognition, right? So for example, one big problem that you come across in adversarial machine learning is that you know that Google's image search engine, right? Google's image search engine uses some deep network, a deep learning network. Right? Now that deep learning network is open to you. You can use it too. Right? Now one possible thing that you can do, and this is called surrogate data analysis. So what you can do is, you create a set of images, right? By clicking, just go out and start clicking pictures. You give it to the Google's deep learning network and look at the output. Since this is open to all, you can send any image and get the output, right? So what you can do is you can create a training data set. A training data set where you have an image and its label. And this label is generated by Google's deep learning system. So now what you do is you train your deep learning system with this huge data set. You can get better than Google. So now you develop a parallel search engine and make money. But you use Google's network to figure out. So this is called surrogate machines. Surrogate machines, they try to mimic the action of the actual machine. Now that is an example that I took for Google, but surrogate machines can also be used to attack authentication systems. So what you can do is you can, have you heard about autoencoders? You have heard about autoencoders, right? So what does autoencoder do? Or you don't have to go there, not even autoencoder. Boltzmann machine, you know Boltzmann machine? So there are two layers, visible and hidden layer, right? So you learn, and we can discuss these things if you don't know. Maybe we can discuss this later. There is a visible layer and there is a hidden layer, so you do the training. So what happens is you learn the activation of hidden layer, right? That will have the same probability distribution as the input. So now what you can do is you can use the activation and generate an input that looks like it. Right? So what you can do in this scenario is you take this labeled data from the authentication machine. Right? Instead of doing it on a Google image deep learning network, you do it on an authentication machine. Right? So what did you do? You gave it training examples and saw the output. So you found the surrogate data, and then you train your own machine. Right? Maybe a Boltzmann machine. You train your own Boltzmann machine with the training data and output data. Now what you can do is, using the activation function of the Boltzmann machine, you can generate a biometric that is very similar to you. Because it has the same probability distribution. So now this is, I have said that you can use Boltzmann machine, but they also use something called GAN, right? GANs. So those GANs are used to regenerate data which is very similar to input data. It can be used to pose attacks on authentication systems. So this is a huge area of research and very relevant to data mining, but I don't know how much of it I can discuss in this class. If we have time, I would like to discuss all of this, but I don't know if we have time or not. So we'll have to choose. Do we talk about HVM, Lagrangian multipliers, all those, or do we talk about these things? So we'll have to choose. I would personally not like to discuss those Lagrangian multipliers. You can read them in a book. But if we can discuss these things, that's better. So that's why I'm rushing to finish. These are all legacy topics. I could just tell you to read the book. But since this is intro to data mining, I have to talk about this. And if I don't talk about this, what questions will I ask in exams? Right? So I have to also take exam. And the exams have to be easy, so I cannot give research type questions in exams. If this was an advanced course, we would have gone in some other way. But let's continue. We have gone way out of topic, but let's discuss it. So the idea is you need to know you need to know the file. Why? Because you want to know the class boundary. If you don't know phi, you don't know class boundary. And if you don't know class boundary, two things can happen. One is maybe you are an adversary, you want to attack the system. You cannot attack. So that is a good thing that you have kernels. But on the other hand, if you are somebody, let's say somebody figured out the class boundary. You as a defender want to improve the machine. So you want to change the class boundary, but you don't even know it. So that is another problem. So that's why they have some kernel reversal mechanism. They have some kernel reversal mechanism. And there is a method called Nystrom approximation, which you can do to reverse, so to approximately reverse a kernel. So reverse a kernel means you get the phi's out of a kernel. So given a radial basis function kernel, you can get the phi's out of it. So now, so all this information is not needed for your exams. So this is all extra information that. So that is what it is saying, that an important observation is that everywhere, in training phase you need the dot product, in testing phase also you need the dot product. So why do you need to know the phi? So if a function just gives me dot product in kernel domain, that is enough. So that's what kernels do. So kernel xi xj is some function that gives me phi xi dot phi xj. That is the kernel function. Right? And then this kernel function has to be positive semi-definite. That is the Mercer's theorem. So Mercer's theorem says that this kernel function has to be positive semi-definite. Right? So this is the Mercer theorem. So the function k is a valid kernel if and only if the corresponding gram matrix is nothing, just phi x1 dot phi x1, phi x1 dot phi x2, and so on all training samples. Right? So it's very easy to generate gram matrix. So it's saying that, okay, you generate the gram matrix and it has to be positive semi-definite, the kernel. But why? Again, I can go into that, but that is just mathematics. That won't give you any extra information. Basically, it has to do with keeping the dot product property. Right? That is what it boils down to. So not only dot product property, dot product has to be symmetric, right? So this gram matrix has to be symmetric. Right? So symmetric as well as to maintain the dot product property, you need positive semi-definiteness. But exactly why, we can go into the mathematical details, but I personally think it's a waste of time. So these are possible kernels. If it's a linear kernel, then x dot y, you know x, you know y, so you know the class boundary. Right? If it is a polynomial kernel of degree d, there might be some methods that you can exactly reverse. Say for example square, if it is 1 plus xy square, or no, if it is just xy square, then probably you can figure out. So if this xy square is x square plus y square, norm of x square plus norm multiplied by norm of y square. That way you can approximate. But if it becomes all this radial basis function, it's become very difficult. So there is one method, it's called Nystrom, and it has a very weird spelling. Is it here? It's not here. Okay. You can probably look it up. Yeah, so you can approximate the gram matrix, and you can approximate phi. So there are a lot of papers on that. So you can take a look at that. And in MATLAB there is a specific function that you can use, nice term approximation. But that is not important if you want to succeed in exams. So the next question is, how do you do multi-class SVM? Very simple. You can take many approaches. First is you can have a one-on-one approach, so which means that if you have 3 classes, you take one class and the other class is not that one. Right? So if you have class A, B, C, you can first do an SVM by labeling B and C as not A. Right? The A versus not A, and then you can do B versus not B, and you can do C versus not C. So whichever one has the highest is away from the margin, the highest that gives you the result. Or you can have just A and B and do an SVM between them, and then B and C do an SVM between them. So that is what is called one against the rest or one against one approach. So multi-class SVM is not, it's just an extension of the single class. So then it gives an example. You can go over the example. Yeah. So let's go over the example. So consider a multi-class problem where these are the class levels. There are 4 class levels, and suppose a test sample is classified as what is Y? The class levels are positive and negative, and Y's are the elements. Right? So so there are 4 dimensions, right?
There are 4 different classes.
Okay, I am not prepared with this example. So if I will discuss this example, maybe I get prepared and then I discuss this example. Right? So I will come prepared next class with this example and we will discuss this example. So this is just to summarize that it wants to find out the maximum margin. Right? It's a maximum margin classifier, and the objective function that it uses, it is the L2 norm of the W, and it wants to minimize that. So basically, SVM assumes that if you go to a higher dimension, then you can always classify a data set using using a line. That is the assumption of SVM. Now, one thing I want to discuss, which is not here, again coming back to the adversarial machine learning concept. Right? Let's say you have a biometric authentication system, or a facial recognition system, or whatever. And let's say SVM gives you excellent accuracy. Every time you get recognized, and any other person, every time they get cancelled, they don't get into the system. On the other hand, you have a knife-based classifier. We have discussed knife-based. Right? On the other hand, let's say you have a knife-based classifier. Which one will you use? No, but the knife-based classifier is not as accurate. So which means that it rejects more than it accepts. So if it is a different person, it will definitely reject it. But if it is the same person, maybe you have to take 2-3 tries. Right? But SVM, if you are the person, then 99% of the time you will be accepted. Right? Which one will you choose? What? Why?
Because these have relatively smaller decision volume.
Relatively smaller, what? Easier, simpler? No, but if you train SVM, then it's just a matter of multiplying with W and adding D, and you are done. So testing of SVM is very easy. Rather, knife-based might be difficult because you have to figure out Gaussian variables and you have to figure out class probabilities and multiply with them.
So we don't want false positives in biometry.
So, okay, now I promised that I will show you one thing, but I didn't show, and I think you have forgotten that promise. So, but let's show you. I have it. So I promised that I will show you the class boundary of naive Bayes. Did I promise in this class or some other class?
It was this one.
It was this one? Okay. So let me show you the class boundary, and then you will have this answer. Okay. Oh. So this is a EEG authentication mechanism. EEG means we use brain sensor, and we want to classify whether it's you or not, right? Using brain signals. Now this is a naive-based classifier trained on the brain signals of 10 people, and we want to classify them one by one. Right? Now this is only showing in 2 dimensions. Now we extract a lot more dimensions, like 10, 12 dimensions. But just for the purpose of showing it, we have in 2 dimensions. Right? So what are these circles? So if you consider naive-Bayes classifier, what does it do? It approximates Gaussian distribution, right? So if you are looking at Gaussians, we have discussed this, and it assumes that given the class, these are conditionally independent, right? So you might as well just look at one dimension at a time, right? So if you look at one dimension at a time, say this is the one for class A, and this is the one for class B. What is the class boundary? This one, right? Because at this point, the probability is same. Class A's and class B's probability is same, and assuming that class A occurs the same number of times as class B, right? So if that is the case, what if I increase the dimension, make it 2 dimensions? But how will it look like? It will be a 2-dimensional Gaussian. Right? It will be like a hat, Mexican hat. If you look at Mexican hat from the top, so you take the hat and you put it and look at the top, what will you see? Circles, concentric circles. What does each circle mean? Equally probable, right? Any point on that circle is equally probable. So that is what this figure is showing. So this figure shows, so basically the distributions are out of the page, no, not page, out of the slide. So you are looking at from the top. So these are all concentric circles. So each circle, any point on that circle represents equal probability. So now what happens? So this is class A, that is class B. So the concentric circles, right? So this concentric circle is class A. And this concentric circle is class B. Right? Now what it means for this circle to intersect this one? What does it mean? What? Class boundary. Right? So class boundary, which means that this is equally probable to be classified as A or B. So now, what is the class boundary here then? How do you figure out the class boundary? You have to intersect Gaussians. So you have to solve the equation that one Gaussian is equal to another Gaussian. What is the x? So what is the locus of the class of x when 2 Gaussians are the same? Turns out that is an extremely difficult problem in high dimension, and it results in very, very weird structures. So one structure is this. Until what time is this class? And it's 7:08 or 7:15? Okay, so I have 7 minutes. Okay, so it gives rise to very weird structure. So what is this structure? These red dots are the class boundaries. So this is, if you do the math, and we had done the math in some paper. So if you do the math, it turns out to be a hyperboloid, which means an n-dimensional hyperbola. That is just for one case. Now if you go to a separate, so that figure is another 2 dimensions. So we have 10 dimensions. This is one choice of 2 dimensions. This is another choice. So different. So F1, F2, and that is F3, F4 maybe. If you look at that, that gives an ellipsoid, the intersection of the Gaussians. That is an ellipsoid. So if you look at this feature dimension, the class A, anything that gets classified as class A should be in this weird structure. It's like a semicircle but then cut by a hyperbola. A semicircle cut by a hyperbola. Whereas this is an ellipsoid. So if you combine these dimensions, who knows how it looks like? An ellipsoid combined with a hyperbola, extremely complex. So using knife-based classifier, you get extremely complex class boundaries. Okay? And potentially what happens is that your acceptance rate decreases. Why? Because very small area is devoted to the actual class. So you can get very restricted area. Right? So one drawback of knife-based classifier is that you get higher false rejections. And you get higher false rejection. But on the other hand, a good thing about it is you get lower false positives. So if you are a different image, for lower false positive means a donkey doesn't get classified as you. Right? And so, but on the other hand, same data, if you look at SVM, this is SVM. Right? This is like RBF kernel, SVM using RBF kernel. So if you do the kernel approximation method and find out the phi, you can get the class boundary, so that gives the class boundary. Again, it's a weird class boundary. It's not a closed structure. There are 2 lines, one this line and then that one. But what we found out is that the client class C, or one of the class, the class that is important, often that is called the client class, and the class that is not important, that is called the void class. Right? The client class is huge. There are huge empty spaces. Right? So what does it mean by having huge empty spaces? It means your acceptance rate will increase. Right? So with an SVM, more often than not you get accepted. But the problem with that is that the false positives will also increase. Right? So if you are given an SVM that accepts you all the time, you are very happy with it. On the other hand, you are given an NBC, you try 2-3 times and then get accepted. If you are worried about your privacy, you won't use SVM. You will use knife-based. Right? Now this type of analysis is very recent. Maybe the last 2-3 years. So in 2017, there were, this 2018, right? Yeah, in 2017, there were 160 papers just discussing this aspect, adversarial machine learning. Right? So it's a very hot topic, and it's very related to data mining. But I don't know how much I can discuss here. So with that, we have finished SVM. So next what we'll do is, I will go back to neural networks. Actually, I will go back to knife-based classifier. And I will go back to knife-based classifier, and we'll talk about Bayesian networks, that is belief networks. Then I will talk about deep belief networks. Then we will talk about Boltzmann machines, restricted Boltzmann machines, and slowly we will move towards deep neural network and talk about autoencoders or all that.
What's up?